Howdy, folks. Welcome back to another CS128 honors lesson. Today, we'll be discussing parallelism and concurrency. As many of you know, I'm extremely excited for this unit. Parallelism and concurrency is really one of my major focuses in my work. And so I'm excited to start discussing this over the next 2 weeks. And I hope to convince you that it is sort of exciting and important as well. So, without further ado, we'll go ahead and get started. Our goals for today are to introduce the ideas of parallelism and concurrency and how they relate to Rust. Specifically, we'll first analyze sort of why parallelism and concurrency is hard, and then how Rust makes it easy, and then we'll just take a brief glimpse on how to actually implement it in Rust. Just a heads up, this lecture is probably going to be a little long. I apologize. There's a lot of content to cover, but stay with me, and yeah, I think it's very exciting, so I don't feel that bad. Okay, don't forget, homework 7 is due tonight. MP2 is due 3/4. MP3 releases 3/3. MP3 is our last MP, and so after that, we're doing final projects. So maybe start to brainstorm final project ideas in groups a little bit, but you still have about 2 weeks until that's really important. Okay, so first, some quick questions for you. Explaining how lowercase works for characters. There's some very useful functions you can use to uppercase to lowercase, is uppercase, is lowercase. I'm pretty sure this answers your question, but if not, let me know on the Discord and I'm happy to elaborate. Quick refresher on unwrap. I do also have some discussion on the second part of this question, which is the difference between asref or the asref trait and the borrowing or the borrow trait. I moved this to the end because this lecture is already long, and this is an additional long discussion. I think what I'll do is I'll record this separately and just sort of post this if anyone's interested. It's sort of a weird niche tangent on some really complex Rust for some reason. But okay, it was very exciting for me to learn about too. So, quick refresher on unwrap. It's very common that we have some operations that might fail. So if we try to read a file, but that file doesn't exist, we don't necessarily want our program to panic, so we might want to create that file if it doesn't exist. So, maybe normally we would return, some like string reference, which represents the contents of that file. If the file doesn't exist, it doesn't really make sense to return an empty string because the file doesn't exist. It's not empty, right? An empty string would sort of represent the file does exist but has no text in it. And so what we can do instead is return, result t. So the result and then, some template class or some template type. Then we can check if what we have is okay or an error. If it is an error, maybe we want to create that. If it is okay, then we want to probably, get the contents out of that. And so we can use unwrap to unwrap the okay type into the t. Or, potentially if we do want to crash, if this file doesn't exist, maybe we want to terminate, then we can unwrap the error type and we will throw this error, whatever is inside of there. Okay, so really, unwrap is just a tool to unenumerate something. So if we have some result that is okay or error, then we can unwrap it and just get the contents of that okay. Similarly, if we have some option type, then we can unwrap the sum and we get whatever's inside the sum. Of course, we can't unwrap a none because there's nothing to unwrap. And so if you try to unwrap a none, then you will receive an error, which is also good because we can check if it is that beforehand. Okay, that's pretty much it for unwrap. Let's get started. Oh, quick updates. I have a new build, new setup. We'll do a quick sort of tour. Okay. I got a new laptop, so here's the new setup. It's very exciting. I think another person also asked if I had an Ethernet cable running behind me. The answer to that is yes. I do have an Ethernet cable running behind me, and I use it for fast internet. Okay, I'm probably going to turn my camera off for the rest of this lecture since I think it gets in the way, but hopefully that shouldn't be too bad. Oh, also another one, how do we go over clone? I really encourage you to go back to the borrowing lecture. I think it was number 6, 7, something like that. I really discussed that much better here than I have time to do since this lecture is already long. But the TLDR is you can call .clone, and we will perform a deep copy of something. So if we have some, capital S string that some variable has ownership over, we can call .clone, and we can create, okay, let's just say this as A, B, C. So we can call .clone, and we will get a new capital S string that says the same thing. This is distinct from taking a reference, which I'll do in pink. If we took a reference, then this variable would point towards the same location. And so then, we don't necessarily have ownership over this. And so this variable might edit this to say B, C, D, in which case this would also say B, C, D. But in this other case, since we cloned it when it said ABC, it would not change. So there's some subtle differences here. Well, okay, the major differences are that we have some new location in memory. I also want to discuss that, I talk about this in that same ownership lecture, but there is some distinction between clone and copy. Basically, clone is some deep copy. So think if it's on the heap, we'll go into the capital S string and, really create a new capital S string with the same data. And copy is usually a shallow copy. So basically, like a reference, copy is generally not used with things on the heap, but it is used with things on the stack. So I32, tuples, string references, lowercase, I should say, string references, things that we know the size of. And this is because if we have something that says like let x equal 5, let mutable x equal 5, we'll say, let y equal x, and then we'll say x equals 6. Of course, y here is still equal to 5, not 6. Right? Okay. And this is because it implements the copy trait, and it knows, okay, you don't want, y and x to point towards the same location. Rather, you want y to point to some new location that has some data inside of it, the same data inside of it. And so then when we change x to say 6, y remains the same. Okay, not my best 6, but you get the idea. Again, go to the ownership lecture. Okay, let's get started with the real content today, y concurrency. So I'm actually a computer engineer, not a CS major, as some of you may know. And so I like to sort of approach this from a why this is important standpoint. So we've done our best in computer engineering to make CPUs and computers as fast as possible for the past 50 years or so. And this is sort of what that looks like. So there's a lot of trends. The number of transistors in a CPU is still exponentially growing. A lot of you may have heard of something called Moore's Law. This is really transistors per area. This is starting to slow down, but okay, don't worry too much about that. That's not what the topic here is. But what I really want you to pay attention to is the fact that single-threaded performance is starting to taper off. Frequency has tapered off. And the number of cores in the CPU is really starting to rise pretty dramatically. And so nowadays, you've seen these modern AMD Threadripper CPUs that have something like 128 cores, 64 cores, hyper-threading, all this crazy stuff. And really, we want to be able to make use of all of those because 99, well, okay, I don't know the actual percent, but a large percentage of programs that you write are single-threaded. In fact, if you don't do anything, it's probably single-threaded. And this means, you have sort of a single core that is executing instructions one at a time. And, it has to handle one thing after another. And, the performance, single-threaded performance is tapering off. And so 20 years from now, so 20 years ago was, what is this, like 55 times 10 to the 3? And nowadays it's 10 to the 5, whatever metric this is. We were able to make things 20 times better from 20 years ago. 20 years from now, single-threaded performance is not going to be 20 times greater. It might be 2 times greater, hopefully, right? Unless we, have some major technological breakthrough. But it's really critical that today's computer scientists, you, are writing code that is able to leverage multiple cores, that is able to be run on, in parallel, that is able to be run concurrently, and is able to continue to sort of increase performance years and years and years from now, right? And, I think a great quote that I like to steal from ECE 408, Parallel Programming, is this, is scalable algorithms and libraries can be the best legacy that we can leave behind from this era. And so what does this mean? It's really, really important that we write code that is fast in the future. If we have a computer that should be 100 times faster 20 years from now, we want our code to run 100 times faster. And if you're writing single-threaded code, that's not going to be the case. And so focusing on making sure our code can scale and is in environments where we can leverage compute of the future that is going to be faster, that will probably have more cores, is really, really important. And I hope to sort of convince you of that over the next, couple lectures. So why don't we do this? Why isn't every program we do automatically concurrent? Well, the answer is that it's very hard. I'll give you sort of this quick example. We have one process, it reads and it writes, very simple. But the moment we have a second process that interacts with that same data, a myriad of issues arise, what we'll call race conditions. Okay, and this means it really matters how these things interact or how these things run that changes the final answer. And so let's say this goes first, and then process 2 goes, and then this goes. Our answer is 1. But instead, let's say that this reads, and then this writes, and then this writes. Then the answer is 10. Let's say that this goes first. So the answer could be 1. The answer could be 10. Let's say that this goes first, and then it reads, and then it writes. Then the answer is 11. And which of these is correct is my question to you. The answer is, any of them, none of them, there's no answer. We don't know which one's correct. And all of them could happen. And if this code were to be deployed, all of them would happen. So, obviously only one of them would happen at a time, but it's up to your operating system's scheduler to determine which of these happens and in what order, right? If perchance, you press some key right here, and then this thread has to go deal with that key press, and then it decides instead of returning to this line, it returns to this line over here, then, then we'll get what would we get? We would get a 1, right? And so we don't know which of these is correct, but we do need to handle it. So one of these needs to happen. We need our programs to be deterministic. And so let's analyze these problems more deeply. There's sort of 4 cases that arise. The first one we looked at, which is race conditions. Generally, this happens when you have 2 resources attempting to read and write at the same time. And basically, when one thing writes, one thing might have already read some stale data, and things explode, right? And so I want you to sort of pause for a second and brainstorm some concepts on how we can fix this, how we can make this not occur. Okay, well, all we need is for this to be deterministic, right? So as long as one of these things always happens, it's fine. And we can determine which one that is based on how we write the code. And so the first sort of easy example I'll give you is what if we just say, whenever thread A accesses a resource, it will prevent any other thread from accessing that resource. So if thread A accesses 1, thread B cannot access 1. It has to wait. Okay, this is very common. This is called mutexes or mutual exclusion. And so thread A accesses, some resources, and thread B accesses some resources. And then thread B says, okay, hey, I need, let's say thread A says, hey, I need access to resource 3 to continue my operation. Resources could be, many, many things. We'll just say that they're, I don't know, numbers, right? But thread B is using that. And so thread B is going to say, no, you can't have access. And then on the next cycle, thread B will say, hey, I actually need access to resource 2 to finish my operation, and thread A will say no. And then thread A is going to try to do its work again, and it's going to try to use resource 3, thread B will say no, etc., etc. And so this will happen forever, and this is called a deadlock. So we need to be able to share things a little bit, right? Deadlocks can occur, they're bad when they occur, and your computer just loops forever and doesn't get anything done. Okay, so that's bad. So what if, okay, how can we fix this? Let's brainstorm. What if anytime you ask for some resource, we just give it to you, right? So we'll relinquish access whenever you ask. Okay, and let's see what happens here. Okay, this is what we call a live log. So thread A uses resource 1, and then next cycle thread B, says, hey, can I get resource 1? And thread A says, yeah, sure, you can have it. And then thread B tries to start working with resource 1, and then thread A says, hey, can I use resource 1? And thread B relinquishes access. And now thread A has it, and then thread B, still needs resource 1 to finish its work, and so it'll request, and okay, you see what's going to happen here. They're just going to go back and forth requesting and not actually getting anything done forever. It's called a live lock. Okay, so how can we fix this issue now? Let's brainstorm. Okay, so what if some threads are more important than others? We don't care how this finishes, right? We just need this program to finish and to finish deterministically. And so what if we just say thread A is more important than thread B, right? We'll assign some priority to the threads. So if thread A has access to it and thread B requests access, it'll get blocked. But if thread B has access to it and thread A wants access, then thread B will relinquish access and thread A will have it. Okay, sure. Okay, we can do this. We can assign priority. Now we get this issue called starvation, which is, okay, thread B will yield access to all of these resources to A, and A will use them and continue using them and continue using them. And thread B is just sitting here continually, requesting access. And so what happens is, thread A does all of its work, and then it relinquishes access, and then thread B does all of its work. Is this not just single-threaded, right? This is effectively the same as being a single-threaded program. We've destroyed any notion of concurrent code. Wonderful. Okay, so concurrency is very hard. We actually haven't really come up with a solution here. In fact, these approaches of mutual exclusion and preventing live locks and deadlocks is hard, and you kind of have to tune it a little bit to your specific use case. You have to be watching out for live locks, watching out for deadlocks, handle those when they do occur. Sometimes you have to allow for starvation, and it's just hard. Concurrency is hard, but Rust makes it easy. So some of the more keen-eyed of you might have realized some of the terminology we're using here is very similar to ownership. And so we go back to our original example. Thread A accesses resource 1, and thread B accesses resource 1. Well, we have two owners over resource 1, do we not? So either thread B needs to be an immutable reference where it cannot write, or thread A needs to be an immutable reference where it cannot write, or both of these can be immutable references, but only one thing can have ownership over this if they're sharing it, right? And so now we have this wonderful case where, okay, if thread B doesn't need write access to this, then it can still read it and get its work done. And if thread A, needs some sort of permission, we can do that as long as it's going to be safe. And so this idea of ownership is actually the same as these ideas of preventing sort of conflicting data accesses. And of course, since it's fixed in this case, we don't need to worry about all those other cases, though you can write Rust code that does worry about those if you need to. Okay, let's go over some quick terminology before we continue. So an operating system is what is running on your computer, of course. Operating systems manage processes. Processes are the execution of programs. Programs are the code, processes are the execution of that code. A process could have many threads. It could have one thread, it could have many threads. This is sort of the classic idea, right? Is we have some heap, some files that contain the program code, some registers which contain things you're currently working with, some stack which contains local variables and, things like that. Local variables, parameters, function definitions, right? Stack Overflow, things like this. We discussed this too in the ownership lecture. And we execute some code. So we go through our code and we execute this line, then we execute this line, we execute this line, and each of these lines are, doing something, right? Reading, writing, incrementing, whatever. Our program can have multiple threads executing similar code or different parts of the code. And in which case, each sort of thread is paying attention to its own sort of portion in the code and executing that code. And this thread over here is executing this. And there's some important things to remember. So different threads have different stacks. So different functions that they've called, different local variables, different, string references, different tuples, different ints, things like that. But they do share the heap, the data. So if you have a capital S string, different threads can all access the same capital S string. But if you have some local variable like let x equal 1, different threads cannot all access this, though they technically can if you wrap it in a box, which we'll probably talk about soon. Okay, and then let's also introduce this idea of concurrency versus parallelism. I'm actually going to do this backwards. So parallelism is exactly what you think. You have two workers, we'll say. Worker, apologies for the mouse handwriting. And they're executing code at the same time. That's it. So, okay, maybe we want to sum all of the elements in some array. Worker 1 will sum all of these elements, and worker 2 will sum all of these elements, and then all we have to do is sum these two elements together. And these two things happen at the same time, and so, our time to run this is like O of n over 2 plus 1. Plus 1 because we also have to add the two results at the end, right? Concurrency is a little bit different. Concurrency is being able to switch tasks when we have some downtime, which is very important. So let's say that we have some code, and we want to read from our hard drive. And this takes, okay, the equivalent of if one CPU cycle is 1 second, this takes, what is that, 1 to 9 months? My thing is in the way. Yeah, 1 to 9 months, which is an extremely long time. We can do many other things in the meantime. So we'll work a little bit on this task, and then we attempt to read from memory. Say we're writing to a file, right? This takes a long time. Okay, so we send that request out, and now the hard drive is dealing with it. Normally, we just have to wait, and then we can continue execution. If we're writing concurrent code, our CPU in the meantime can work on this task. And maybe it takes a break of that and starts to work on this task, and then this task finishes, and now it goes back to this one eventually, right? And so we're able to make use of this downtime, which is very powerful and can really improve performance. Okay, and then one last sort of point that I want to go over before we look at some code examples is that effective concurrency, writing concurrency that's actually good. We saw examples when you have this prioritization of your different threads. After we solve the live lock issue of ineffective concurrency, we'll say. Effective concurrency is highly dependent on effective communication. So your threads need to be able to communicate well. And there's really two major ways to do this. And these two ways are message passing and shared memory. So shared memory is sort of as it seems. We have two processes, two threads, whatever it may be, and they have some region in memory that they can both access. Okay, and so process P1 says, okay, in our example of summing up some long piece of the vector, P1 has a byte here and a byte here. And this byte represents its sum so far. And this represents, we'll just say this is 0 or 1, representing if it's done. Right? And so when this finishes, it'll say 52, I'm done. Right? And then P2 has its own, and it'll say, it'll say, 108, and I'm also done. And then some other process which spawned these, or one of these processes, can continue to execute the code that says, hey, if this is 1 and this is 1, add these two numbers together, 160. Oops. Where's my erase button? There it is. Okay, 160. The second sort of option is what we call message passing. And so this is when we have some thread, and they can sort of send messages to one another. And so this one process says, okay, it'll do its sum, and then it'll say, hey, do I have any messages from process 2? And process 2 maybe sent a message that says, hey, my sum is 52. Okay, I think process 2's sum was 108, so I'll keep it consistent. Hey, my thing was 108, you're good to go. If that message is there, then we can add those two things together. If that message is not there, then maybe we want to wait for that message, right? Or maybe we can do something else in the meantime, and then go back and read their message. Okay, so lots of options. And we'll analyze these more deeply over the next couple lectures. Okay, very cool, Eustis. How do we actually do it? How do we write code that uses concurrency? Okay, so here's a quick snippet, a very basic snippet. Let's analyze sort of some of the major parts. So, of course, we need to import things. We'll use duration just for this example so that we can have a little pause and utilize that concurrency. Then we can, we import the thread library, the standard thread, because we need to spawn threads to actually perform this work. We call thread spawn. So thread spawn is a function which takes in what we call a closure, which we'll talk about in just a moment. I know it's weird syntax. And this says, hey, I want to execute this code on a different thread. Okay, now what the heck is a closure? I know you're waiting for it. Okay, a closure is an anonymous function that can capture its environment. So let's do a quick aside on this. So what does anonymous mean? Well, anonymous just means this function doesn't have a name. So this function's name is main. This function does not have a name, but it is still a function. Rather, maybe you can say that the function's name is whatever this variable is, but fundamentally, it's a nameless function, or at least it can be a nameless function. So in this case, what we're saying is, okay, I have some function, which I'm going to refer to as closure. This takes in some variable called num. It returns an int, and this is what it does. It calculates over 2 seconds and then returns, I plus 1. Then we can call it, so closure, because we are calling it closure here. We give it a 3. 3, we say, num equals 3. We wait 2 seconds, and then we return 4. And so this would print 4. Okay, that's pretty much it. There is one other part that we need to analyze, which is this capture their environment part. Basically, when we talk about closures, I don't want you to think of this as a closure. I want you to think of this as a closure. Okay, closures can capture values from their scope where they're defined, which is unlike functions, right? If theoretically I had like some int x equal 5 here, we cannot say main x and then this main will automatically infer that these two x's are the same. That's not how that works. Closures do work like that because they're sort of inline and anonymous, and we'll look at sort of why that matters soon. Okay, and just because syntax can be weird, I want to sort of show you this evolution from a function to a closure, to the closures that we see at least. So we have some function, just like normal, it takes some parameters, it returns some value, this is the code inside of it. When we want to turn it into a closure, all we have to do is, change this from a function to sort of an inline expression and say let this closure equal, these are the values that it takes in, this is what it returns, this is what it executes, don't forget the semicolon, because let, right? Okay, syntactically we can shorten this a little bit, right? We don't always need this in a function, we don't always need this in a function, we also don't need them in closures. So we can just say, I have some function that takes in a variable x and returns x plus 1. Okay, and then to take things even further, though I don't necessarily recommend you writing your code like this because now it has to be single-lined, I have some function that takes an x and returns x plus 1. Okay, let's hop back over. So in our case, we have some closure, which takes in no variables and executes this for loop that prints I and then waits 1 millisecond. Similarly, outside of this, so we spawn this thread, and then in the main loop, we say print 1, 2, 3, 4, 5. Okay, so what happens here? Take a moment, pause. I have some examples on the right. What do you think happens? Okay, the answer is either. We don't know. We don't have any control over which one of these occurs. Because we don't control when our operating system schedules these things. And so both of these are valid results, and both of these are copied from times I ran this exact code. Now, there's a lot of interesting questions that are raised. Notably, why doesn't this get to 10? Right? This time it gets to 8, which is pretty close, but then it stops. This is because, very simply, when we spawn this thread, this handle variable takes control over it. And then we go down to this for loop, right? This is in the perspective of thread A, which is executing kind of the main function. We spawn this thread, we do this for loop, and then we end this for loop and we leave this function. When we leave this function, we drop the handle, right? When values go out of scope, they are dropped. We remember this from ownership. And when we drop a thread, a handler, the thread is killed. So the thread no longer executes because we no longer have any place to sort of receive what it might send. Okay. Of course, there is a way to get over this, which we'll look at in just a moment. But first, let's look at the perspective of thread B. So thread B doesn't exist until thread A spawns it. Thread B does a for loop, and every time it's printing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If thread B is killed, then it's killed and it doesn't get all the way to 10, which is what we see in these cases. So if you want it to finish, you can call .join on the handle. .join will return a result, which will either return, whatever the function returns, or it will return, so it'll either be okay of something the function returns, the thread returns, or it'll be error if the thread panics, which is why we unwrap. Of course, if the thread panics, we might want to have our main thread panic, or we might not want to have our main thread panic. Because I'm just unwrapping here, I'm saying if this for some reason panics, then I want my main thread to panic too and stop execution. So what this will do is this will execute, okay, thread A does 1, 2, 3, 4, 5, and then it'll wait. And it'll wait for thread B to finish. So thread B will be able to get all the way through 1 to 10, and okay, maybe we get something like 1, 1, 2, 2, 3, 3, I'll just say 4, 5, 4, 5, 6, 7, 8, 9, non-inclusive of 10. Okay, so of course we don't know the actual order, right? It's down to the operating system to schedule it. Okay, what happens if we move it here? Okay, a lot of you might say, okay, this will clearly do 1, 2, 3, 8, 9, and then it'll do 1, 2, 3, 4, 5. These are from spawn, and these are from main. And you would almost be correct, except I sneakily changed this 9, or from this 10 to a 9, and so it'll only get to 8. So stay on your toes. But yeah, you're absolutely correct. It'll print all of the ones from the thread B before thread A does any work. Of course, maybe this isn't really peak efficiency, right? But who cares in this specific case? Okay, that's all. I'll see you all on Thursday. If you want to learn about that asref versus borrow function difference, then stick around for a couple minutes. And oh, I forgot I was going to do this as a separate video. Okay, I'll do that as a separate video. I hope you all are all excited about parallelism. Let me know if you are. If you're not, then I'll talk more about why it's so important and so cool. That's pretty much it. Okay, see you all around. Bye-bye.